Hello, and welcome back to episode 2 of the Munters Cooling Innovation Day. Up next, we have a fantastic session which will take place as a panel discussing air and liquid cooling predictions for the future. For this discussion, we're delighted to welcome Nick Casale from KW Mission Critical Engineering, Seth Davis from McKinstry, Stuart Lawrence from Stream Data Centres, Dr. Tim Shedd from Dell, and Keith Dunnavant from Munters, who will be moderating this panel. Without any further ado, I'll hand over to Keith.
Thank you, Tim, for that excellent presentation. Really good to see this analysis finally get done. Sometimes I find that the simplified analyses, as you have eloquently done, lead to the most meaningful results. Tim, I'd like to start off with a number of questions directed to you.
Okay.
Specifically, to start, you talked about direct chip cold plates, both single phase and two phase. And I'm curious if your simplified analysis took into consideration either for single phase, it took into consideration jet impingement technologies versus more conventional direct to chip single phase.
So indirectly, yes, we used in the analysis typical thermal resistances that are pretty typical of technologies available today, regardless of exactly the internal structure of the cold plates. At this time, we have not seen significant variation from those numbers in the model. But we do anticipate technological improvements as things move forward. So perhaps we'll see some significantly improved resistances in the future that might shift those numbers. But as we saw, direct-to-chip cooling is already looking really good. So that will just be kind of enabling even more margin into the future.
Good. And similarly on the two-phase direct-to-chip, you've got pool boiling technologies, microchannels, and things like that. I'm assuming the same applies.
Yeah, yes, exactly. So what we've seen in the two-phase space, the physics are at root very similar, whether I have a pool boiling or a flow boiling, at least as far as getting heat off the chips. The benefit of the two-phase technologies is that you do get this thermal resistance that decreases with increasing heat flux, and that appears in both the pool boiling and the flow boiling cases. So again, to first order, it's captured in the model, at least with technologies at the current state.
Good. And then lastly, with the immersion analysis that you did, there are in the industry today some hybrid versions of immersion where it's kind of like a jet impingement where the dielectric fluid is sprayed directly onto the chips, and I'm assuming that would give a different result than the evaluation that you did, which is more like a tank with the servers immersed.
That's correct. We are aware of some innovations in the space, especially in the it's often called an in-rack or in-server immersion technologies. And we are aware that there can be some improved thermal resistance at the package with those technologies, but we don't have our own test data for that, so they weren't included in this study.
Gotcha. There are, speaking of hybrid solutions, there's some solutions out there in the market today that they're liquid direct-to-chip cooled, but there's no working fluid going in and out of the racks. It's all self-contained. So there's cold plates to pick up the heat through a circulating fluid within the rack or within the server, and then that heat is transported to an air to liquid heat exchanger, either within the server or as a rear door heat exchanger. And it seems to me that as a bridge type solution may have some legs to to take care of customers that have a small percentage of their workload that need to have liquid cooled servers. Would you say that's accurate?
Absolutely. So as I noted in the previous analysis, air cooling, especially for dense applications or high-powered processors, is just limited by the physics of getting enough air to the processor. However, if we can collect the heat using a liquid and then pump that liquid to a radiator or a heat exchanger that's much larger, we can effectively spread the heat out and use reasonable airflows to remove that heat. So we call this in the industry liquid assisted air cooled, or LAC solutions. And you're correct, there could be closed loop solutions inside of servers and open loop solutions that connect to an apparatus that might sit alongside the rack or within the rack that can cool multiple servers. And we are absolutely seeing this. There are many customers who have implemented extremely efficient air cooling strategies in their data center with fresh air cooling and other technologies. And this sort of LAC solution can extend the lifetime of those data center facility level solutions, another generation or two or three even. And so absolutely we're seeing some demand there. And we're seeing that also not just in single phase liquid cooling, but also in the two-phase DLC. We're also seeing some solutions like this. So absolutely, I think a key transition technology, and we do see significant growth there for the foreseeable future.
Good, thank you. One of the challenges that I see for the others on this call, in particular, Stuart, Seth, and Nick, as design engineers, is trying to come up with the right fluid temperatures as they are selecting chillers and piping and everything. Selecting the right types of cooling apparatus, and not only that, but understanding what kind of delta T's they should be designing around, which dictates the flow rates. Your analysis showed that there can be, a bit of a variation. So I don't know if you have any guidance that you could offer to the folks on the call as to, if you were in their shoes, what you would suggest they might design around, assuming they don't have specifics from the customer yet as to the exact type of cooling.
Yeah, so it from a data center facility point of view, customers who talk to us at Dell Technologies, they're often approaching us with questions about how to improve their sustainability, lower their energy consumption, and to achieve practical densities. Most of our customers aren't looking for 100, 200 kilowatts in a rack. They just want to use the space they have as efficiently as possible. And so there are a lot of parameters there. You all know, as I do, that raising cooling, facility temperatures is a benefit typically, but to a point, right? If I raise the temperatures too high, then my server fans start to increase and power consumption can kind of level out. Our analysis that I presented at the end there showed that about 27 degrees Celsius, or what is that, about 80 to 85 degrees Fahrenheit in the data center is really a reasonable temperature. I think that's also a good ASHRAE recommendation. But as far as liquid cooling to the chips, there's a further movement, and I believe was just presented recently through OCP, looking to the future. These chips that many of our customers want to use for AI, machine learning, and so on, are going to be very hot and are going to require that liquid to the racks does not exceed about 30 degrees Celsius, or what's that, about 80, 86, 87 Fahrenheit. And so I understand that could be the new kind of maximum liquid recommendation for these dense racks. So keep an eye out for those recommendations as they come out. On the whole, it looks like 25, 27 degrees facility water, so some mixture of maybe cooling tower water or dry cooler water with trimming with compressors. That's going to be a good temperature for handling future processors as we look, 5 years or so into the future.
Good, thank you. When you do go direct to chip, especially with cold plates, there is some residual load that's got to be picked up by the air. Less so for immersion solutions, but what do you see as the typical residual for cold plate installations and for immersion pods?
Sure. So this is a complex question and varies quite a bit. So the warmer I can run the data center facility, the more heat I'll push into the liquid. So that we assume to be conservative that we typically only pick up about 65% of the heat into liquid when we have cold plates on an otherwise air-cooled server. But that assumes really that I've got 20 degrees Celsius air coming into the server. If I've got warm air coming into the server close to the water temperature, actually I'm going to capture more like 70 to 75% into the liquid. And then I can always put a rear door heat exchanger on the back and capture all of that heat into liquid out of the rack combined between the two, or just with the rear door heat exchanger or in-row cooler. So there are strategies to do that with liquid, with water. As far as immersion tanks, they are capturing virtually all of the heat. There may be a few components that can't be immersed, and those will release heat back into the data center directly. Indirectly, my understanding is the loss is very low. I don't know the exact number. I will say it's less than 5% of the heat is lost from the sides of the tank typically, but I don't quote me on that number precisely. But again, that also depends on the difference between the liquid temperature and the ambient. So a strong advantage of immersion, and one of the reasons why proponents have been working with it for many years, is this fact that you can capture essentially 100% of the heat directly into the oil, which then is transported out of the facility directly without any air exchange and very little heat leakage to the facility. So definite benefit of immersion there.
Good answer, thanks. And then the last one I want to throw at you is two-phase immersion. Seems to have a lot of appeal, but I'll show my lack of knowledge about that solution and ask the question, how do you contain the vapor? How do they contain the vapor? And is it fully contained? And if it does enter the room, are there any health risks associated with it? And what's the frequency at which those dielectric fluids would need to be changed out?
Yeah, so I'll have to leave the details of that to the actual manufacturers. But my understanding, I've seen several implementations that do successfully contain the vapor, which is, as you noted, it's required as much for maintaining the fluid and not losing the fluid, because it's a rather expensive, maintenance item, as well as for potential safety concerns. From the safety perspective, there is concern because most of the fluids are PFAS fluids, so there's concern about long-term health risks that haven't been fully quantified yet, to be completely clear, but have been strong enough that there have been some issues raised. The implementations I've seen, however, do tend to capture that vapor, whether it's in a rigid container and pressure control, kind of continuous condensation, or through expandable volumes that can capture that. And so I'm not aware actually of significant issues with vapor escape or challenges that would present. So I from that perspective, I believe that two-phase immersion is considered safe and scalable in the data center.
Good, thank you. Okay, moving on, Stuart, I've got a question for you, and that is with what appears to be some level of uncertainty. How do you approach your current data center designs to accommodate the future implementation of liquid cooling by your customers?
Yeah, Keith, great question. It's tricky for us at the moment, right? We are a wholesale co-location company, a developer. So we're building for the large enterprise hyperscale type customers where scale is important. It's all about scale. So it's not about a 1 rack, 2 rack HPC solution. It's about how do I put out 8, 10, 20, 40 megawatts of this equipment in a relatively short period of time. And so I think that's the juxtaposition that you kind of have to understand our lens, sort of the lens we're looking through at solving this problem. And right now, our approach is to build out a traditional air-cooled environment using large fan walls, flooded design, hot aisle containment, maybe 6, 8, 10 megawatts in a data hall, somewhere around the 250 to 300 watts per square foot, with a view to replace fan walls with CDUs for that closed secondary fluid network into the data hall, using overhead conveyance for piping and drops for each rack. And for the most part, what we've seen at least is the plant water being around, typical plant water. Delta T's vary somewhat, and that's creating a little bit of havoc for us, right? Because typically air handlers are piped with 65 to 68 degree water, trying to hit somewhere in the 75 to 78 degree air side temperature, using a 20 degree delta T on the air side, but on the fluid side, seeing lower delta T's. And so the leverage that that the plant water against the secondary fluid network becomes critical, and sort of the design of those heat exchangers and the size of those pumps to meet that. So a little bit challenging right now. I'm looking at lots of different technologies to try and solve for this. Tim shedding some light on the proportion of liquid cooled or direct to liquid versus air cooling is helpful for us, because we've been basing around 60% liquid, 40% air, under the proviso that if we have to replace more fan walls for heat exchanger, secondary fluid network, or DLC CDUs, we can do so. They take up less area in the gallery. We have to deploy them. So it's a little bit of choosing your design blocks and trying to figure out how you can make them maximum configurable, or maximize the configurability of them, so that different customers with different temperatures and clusters can come into the same space. Configurability is important for a co-location company. So maybe we don't get the highest performance or the highest efficiency, but we're able to configure different customers at different delta T's with different air to liquid ratios coming into the same space, but give them something that works. And then maybe use some rear doors if we've got a little bit too much air, and we sort of have that configurable nature about the space.
Nick or Seth, any comments that you'd like to make on that topic?
Yeah, I think Stuart did a great job summarizing how you accommodate the flexibility that you need to provide a cooling solution for multiple solutions. And really the only way to do it is to start with a liquid cooled heat rejection component, as Stuart alluded to, right? And so whether that's chill water, chill glycol, or some sort of refrigerant based system that has the ability to pivot from air cooled to liquid cool, it's important that you start with the right infrastructure up front. And the bulk of the data centers you're going to see on the market today have some sort of chilled fluid component to them. And what we do is we have a starting point where we have the ability to, even if the bulk of the facility is set up to perform conditioning through air cooled solutions, we have the ability to pivot to water cooled and have those connections up front, so that they can either do one, the other, or a combination of both.
Yeah, I totally agree with what Stuart and Nick said. I think there are 3 things that we're doing right now on our chilled water solutions that are currently for more of a air-cooled solution, but could pivot in the future for direct liquid cooling. One is we're allocating additional space for pumping, because we see that with the higher temperatures, it's going to require a decoupled pumping loop that would operate at warmer temperatures. So having space or having a plan for where that pumping might be located. The taps that Nick was talking about is another one. And then a plan for how we would distribute that higher temperature loop in the space and have discussions of, is it going to go underfloor, or are there going to be like a skid mounted option of routing the piping on the ground and having IT infrastructure above that. So have a plan in place and have discussions of what that might look like. And then the last thing is we've been putting in floor drains in the white space to plan for that future liquid cooling scenario where we now have water in the white space.
It's interesting to me. What are you guys seeing in terms of the future proofing for a rack position? So one of the things that I think is we don't often talk about as mechanical engineers is the electrical side. And I did a little stint with Schneider, and I remember several things coming up around, well, once we get to about 100 amp 415 volt feed, right, or for busway, seems to be a logical barrier, going above that. It's something around 70 kW per rack. Is that sort of where you guys see the rack position topping out in terms of power, if it's a standard vertical rack, or are we still going to go further than that?
Yeah, one thing that we've seen in some of the projects that have come through our plate is it is really noticeable how much less space the direct liquid cooling solutions take up. Like we've seen, like the amount of space that would take up 4 quadrants of a data hall are now taking up 1 quadrant. And so we find that in that direct liquid cooling scenario, there's a lot of extra space that is now in your data center.
Oh, Seth, no doubt. The designs we've worked on lately, the actual fan walls are the reason that even at 40% of the overall load going to fan walls, they are the cause of the size of the galleries and the size of the white space. And we could get 10 megawatts into probably less than 10,000 square feet if we didn't have to deal with the fan side. Mm-hmm. Mind-boggling.
Yeah, we're seeing that the form factor is a lot of the time driven by the generator yards and the utilities coming into the building, unless you start stacking generators vertically, which is something that we've been doing in increasing frequency. We found that over the past decade, the facilities that we were designing around 200 to 250 watts square foot are oftentimes starting to see only about 60% of their white space be utilized by the end user before they run out of power or cooling. And we've been looking at how we can still make use of that space and optimize it for our customers so that they can get the most out of it. But oftentimes they run out of power before they run out of square footage.
Feeding off of that, Nick, you guys are dealing with a whole bunch of different customers and with KW Mission Critical. What percentage would you say of your customers are actually asking you to design in liquid cooling now? And are you seeing a particular solution, cold plates versus immersion, more than one versus another?
Yeah, I mean, historically, it's been in the single digits, and that's even true of what we're seeing today in terms of percentages. It's not nearing 10% yet. The conversations are going in that direction, but we're still in those single digit percentages. And more commonly, when the densities start increasing, we're seeing an ask for close coupled cooling, such as rear door heat exchangers, in lieu of the direct liquid to chip. And oftentimes it's because you can approach higher densities on a per rack basis without locking a customer into one technology or the other. We have been seeing a lot more talk about direct to chip in the past year or so, I would say. But oftentimes they become cost prohibitive for a lot of end users. So I think it's definitely coming down the pipe, but I don't know if that's 1 year out or 5 years out.
Good, thanks for that.
I could probably add a little bit there. We've been fortunate enough with the customers we work with that we've been fortunate to see a few solutions recently in probably the last 5-6 months, where they have an air-cooled version of their cluster and then a liquid-cooled version of their cluster, and they'll say, "Oh, this is going to co-location. You guys get to use the air-cooled version. We're not deploying the liquid-cooled version in our sites just yet, and your sites just yet." And then, but I think, I feel like this is going to be a binary moment. It's going to be one of those situations where if your data center is prepared to accept the liquid cooling version, the day they decide to start shipping that only is the day that you're either in or you're out. And so we're trying to get ahead of that and make sure that we're capable of accepting that as it comes down the line.
Yeah, and in a lot of cases, when it is a liquid cooling application, there is a combination of liquid cooling and air cooling in the same space. And to Tim's note earlier about even when you're doing direct liquid to chip, you still have roughly 20 to 30% capacity in air cooled technologies, and that's not only for the auxiliary heat off of the servers, but also for miscellaneous components in the space, such as PDUs or feeders that do give off a small amount of heat.
Yeah, one of the benefits I saw on the liquid cluster version that I saw was they were able to move the racks much closer together and network fiber. The difference between multi-mode and single mode fiber is order of magnitude, and then if you go to copper, it's even another order of magnitude. So enabling these clusters to be closer together and actually has a big benefit on the fiber switching network side of things. So it's going to be interesting to see how long before they really start saying, okay, let's go this direction.
Seth, do you have any comments that you want to add, or are they?
Yeah, I guess one thing to add is that as we see these direct liquid cooling applications come into existing data centers, I think the trend is they can be incorporated with relative ease if it is a chilled water solution to begin with. However, reaching and gaining the benefits, all of the benefits that a direct liquid cooling could bring, might not always be the case when you implement it in an existing data center system solution. So we might not be able to achieve all those energy promises or hopes that the team has just because of the limitations of the equipment that's already there.
Yeah, you're dealing with the chillers that were selected to provide cold water. You're going to have to put in brazed heat exchangers, and you just won't see the same level of efficiency as designing from scratch.
Correct, because those chillers, most of them that we're seeing have a limitation of how warm they can really run.
Yeah,
Especially the screws. The screws hit a pretty hard stop, and it gets pretty scary if your SLAs are as costly as most of them are.
Yeah, and we don't want to run on the ragged edge. We want stability in the system.
yeah. Back to you, Seth. At McKinstry, you guys are involved in the design and the build, so you're a little more concerned, I should say, perhaps, about the costs and managing those costs for your customers. And we've gone through a period of just extraordinary inflation. In fact, I looked at the Fred index, and what it did in 2021, 2022 has never happened before in history. That slope of price increases in the HVAC industry. So does McKinstry have any special tricks to manage those costs?
Yeah, I'm sure everyone on this call has felt the pain of, lead time issues and inflationary pressures. And as designers that, live in the same room as our construction procurement team and construction managers, we hear on a regular basis kind of the struggles that everyone is having. I guess what I've seen of what the team has tried to do to minimize those pressures as much as possible is move up the big equipment orders earlier in the design process. And so many of our projects now, we are, almost in schematic design, as soon as the basis of design is nailed down, there's pressure to order equipment. And I guess that takes a comfort level with the people ordering it and the people speccing it, and just also heightened communication of like what those performance criteria is, and really nailing that down to the degree that we can order equipment early, and the criteria that we're trying to target in the project. So there's a lot of discussions that are very detail oriented early on in the project that might have come later, but because we're trying to order equipment early to mitigate those schedule and cost pressures, they're being brought to the front of the project. I might add that it might not just be the whole equipment. Another strategy that we've been using is to order the long lead components. Like in a chiller, it's not the whole chiller that takes 60 weeks. It's the compressors, it's the fans. And so we will use a strategy that pre-orders or early orders those compressors and fans to mitigate the schedule and cost pressures, and at the same time give us a little bit more time to figure out the final details of the design, so we're not ordering something that paints us in a corner.
Good. Anyone else care to comment on that? I think you pretty well.
Yeah, I mean, I would dovetail on what Seth said. If you're working with any of the hyperscalers, if you haven't got your ducks in a row with respect to your supply chain at least 2 years out at dozens, tens, maybe even 100 megawatt type capacity, your likelihood of winning a lot of those deals is going to go way down, because their subject matter experts are digging into your design at schematic design level, understanding all the things you have and to make the schedule work. They're looking at your schedules, and so it's going to be interesting to see how this affects the liquid side as we go into more liquid designs. Those components are going to start to stretch out in terms of lead time, and how do we start to form ourselves around being that early, Seth, as you said, in terms of schematic design, picking components. How do we know they're going to work in 2 years' time based on all these moving parts? It's an exciting time to be around.
Yeah, that's a good point, Stuart. If I could just jump on top of that. So we've also had discussions about pre-purchasing. So for owners that have a similar type build in multiple sites and plan to use that similar type build going forward, there's been discussions about pre-purchasing, same sort of thing, equipment or components. And then you got to take your crystal ball of, okay, will those work in all the sites? Will they work at various deployment IT loads? And then in addition to that, the industry is undergoing a heightened sense of a concern on refrigerant type. And so what are the refrigerant types of all those systems going to look like in a year or 2 years' time? So how much do you want to bet against that, or try to predict what that is going to look like?
Maximum flexibility, maximum configurability. I we talk with our design teams and internal engineers all the time, and for me, it's just, don't make snowflakes. Snowflakes will get you in trouble later on down the line when your square peg doesn't fit in your round hole anymore. So I try to, and that's at the detriment of efficiency a little bit, really, right? I mean, if you were trying to be the best efficient system in the world, it would be exactly purpose designed and engineered. So we're in a strange time.
Yeah, it takes a certain amount of discipline to design and build the same exact thing every time. And although our sites can constrain us, we typically, if we have a prototype that we have had the proper foresight to design where it can apply across multiple climates and multiple criteria, we can usually make that prototype fit into the space of the site and within the constraints of the site. But it takes a certain type of owner to have that discipline to not try to reinvent the wheel every time they want to build a building. And the same applies to the design team as well. And some of our customers will actually pre-order equipment and have a certain amount of inventory with all their manufacturers on hand so that they can deploy at the drop of a hat.
Yeah, a small item like that though, one that springs to mind is glycol. You know, you take a system that's designed for 100% water down in Arizona and you say, okay, well, let's move these components to Chicago. Well, you better have a freezing mitigation strategy if you're not going to put even, because now your coils or your heat exchangers aren't sized appropriately because of the glycol derates. And now how do you, mitigate any freeze concerns? So some of these things, I'm in that camp, try to make it as modular and consistent as possible to be able to build at scale in different geographies. But then you've got to have other strategies that you mitigate. So, and I haven't even crossed that bridge when it comes to the liquid side. So interesting to get Tim's feedback on how you guys are dealing with those types of situations.
Okay, this question is directed to you design engineers. When customers are coming to you, would you say they have some level of clarity on the type of liquid cooling that they want to deploy, or are they really looking to you guys to figure that out?
A little bit of both from my perspective. We have seen bases of design that actually give ranges of future direct liquid cooling temperatures for the facility water that they want. But then there's also projects where they asked our opinion and ask us to make recommendations. So we're seeing a little bit of both, I think.
Yeah, so it's going to depend on what customers come in and talk to you about this as well, right? So if it's an enterprise customer or hyperscaler, they're going to know what they want in terms of what cooling technology, what they're going to have in their racks, or in an immersion bath if that's the case. If it's a colo provider, usually they're not entertaining going liquid cooled as a standard. However, they want to have a plan for it. And if they had their choice, most of the time they would choose that their end users come with a direct to chip over an immersion, just because they can more flexibly design their facility to address multiple direct to chip applications. Whereas if you're going an immersion bath route, it takes a little more specific of a design to properly address it. So a direct liquid to chip can be deployed in a rack, as you guys know, and if we build that form factor across a standard rack size, it's a little more easy to apply more generally.
Your chilled water plants today are, I've seen some jobs that come through with no economizing at all. Most seem to have some level of air side economizing. I'm talking about air cooled chillers specifically. And some are using fluid coolers. And I'm assuming you could get a little better optimization of energy if you combined a purpose-built fluid cooler, a dry cooler with a air-cooled chiller. Any comments around that, or pros and cons?
Simplicity and repeatability. Like I was saying before, for me, at least for us, we're using air-cooled chillers with in-series water side economizing as a means, and that strategy changes a little bit when we go to hotter climates where the number of hours that's going to be beneficial drops to a small amount. So that's where I think we sort of got to look at other technologies, and not pumping your company here, but Cycool is an option that kind of changes the narrative a little bit about in terms of what kind of economizer you would look at.
Yeah, I mean, the short answer is that exactly as Stuart mentioned, the air-cooled chillers with built-in economizer are the most common solution that you're going to see on the market today. It gives the best overall combination of capacity density, efficiency, speed to market, and cost that most of our customers look for. However, it's not necessarily the best solution across the board, as he's implied. Fluid coolers and cooling towers do allow for better overall efficiencies, but at the cost of using water. And while we have a power issue in a lot of our markets today, That might not necessarily be the case 20 years down the road, but we are seeing that clean water is an increasingly rare resource that we have, and trying to solve the water issue right now, I think, is a higher priority than trying to solve the power issue. And once we have the power issue solved, maybe the clean water problem goes away as a result by making desalination more viable. But where we are right now, we have to treat that water as a finite resource.
There's a large amount of pressure on removing water from data centers in terms of using it to reject heat in an evaporative process. It's you can, I mean, it's well written about now. You can go and look at any publication and you will find an article on hyperscaler X is removing or transitioning from an evaporatively cooled situation to a air-cooled situation. And I think the liquid-cooled approach is only going to probably exacerbate that. I think as we get higher in temperatures, while it might sound logical to do some evaporative assists in peak times, I think we'll start to, with the renewable energy side of the equation, start to probably rely on a little bit more trim cooling to hit those higher temperatures.
Yeah, just to totally agree with what Nick and Stuart were talking about. Yeah, I think we see two flavors of air-cooled chiller currently for the typical chilled water system. It's the the screw chiller with the water-cooled section on it, and then we're also seeing some mag-bearing chillers that do not have a water-side economizer, but are more efficient at delivering those low ambient ranges. Now, we're also seeing, I think we mentioned it before, there's a limit to how warm a temperature we can bring to those chillers, and that I think leaves a lot of the energy still on the table. But first cost is still king, and providing a, let's call it an energy only solution to a system is still quite a hard sell. If it's not helping with your design day cooling. But as I guess what I see as temperatures, as direct cooling gets more incorporated and that temperature drives up, it'll be interesting to see if there's an appetite for that peak evaporative solution. Because if we can, let's say, maintain the design temperatures for 95% of the year, 95% of the hours, is there an appetite for that remaining 5% to be a evaporative assist that could eliminate or minimize mechanical cooling, DX cooling in the system?
Yeah, and along that point, there have been studies showing that if you can save, or if you utilize a gallon of water at your site, by doing so, you save a certain amount of power. You can save quite a bit of water consumption at the utility plant, where the power is being produced. So you'd have to look at where your power is coming from to see if that applies to your site and if you're actually saving water or not. But there have been studies that have shown that it can be as high as 10x the water saving by using one gallon at your site.
And if there is that appetite, then a site in the southern part of the country is very different than a site in the northern part of the country, where one could be a opportunity for no mechanical cooling solution, where the other, you still have a peak day that has a design temperature of 120 degrees and 99-degree wet bulb, where it's not an option.
Right.
Going back to the chillers and the some of their design limits that you're seeing, both in terms of supply, chilled water temperature, and the return water temperatures. What are you guys seeing as the limits, and does this present a challenge? And do you wish manufacturers could make some new chillers that were more flexible?
We're seeing chill water leaving temperatures as high as 70, and sometimes into the mid 70s, depending on the manufacturer. That seems to be where we're topping out. When you have a built-in economizing coil on the chiller, if you configure it right and control it right, you might be able to to get that temperature even higher, but you would have to make sure that you're designing from that day one. It's not something where you can design the facility around 60 degrees and then try to operate it at 75 or 80. We're seeing delta T's around 14 degrees Fahrenheit. That seems to be the best balance point between efficiency and turn down on the hydronic side. If you go higher than that, you don't get as much turn down, or I'm sorry, you get more efficiency, but you don't get as much turn down. And if you get lower than that, you don't get the efficiency that you would otherwise see. So 14's been our balance point there. In terms of ambient temperatures, we're seeing that most chillers can't really function above 130 degrees Fahrenheit. They can function there. They're not going to get the full capacity. It's going to be a derate once you get above the rated condition. We are working with some manufacturers to get above that condition. They're hardening their equipment in certain aspects, and we have a manufacturer or two that can function as high as 140 degree Fahrenheit, but again, with some serious derate in their equipment.
And I'd add to what Nick said, it seems like the high entering water temperature of the chillers is 90 to 95 is what we're seeing. Above that is starting to cause some issues. And then we've even explored trying to, operate higher when you're in dry cooler mode, or water side economizer mode, but it's that switch over to as soon as that chiller wants to start, having those warm temperatures cause issues. So it really is a limiting factor.
Good. Having water in a data center, and especially running around the racks, is always a concern. Do you guys have any special mitigation strategies you've just deployed to reduce the risk of associated potential leaks?
Few things that we've used, I think I mentioned before, floor drains in the white space. So far, all of our projects, the client is preferred running the piping on the ground, which in most cases is brought back a raised floor to that white space. And then also utilizing kind of sheet metal dams with leak detection inside the dams to try to isolate if a leak does happen, and then early warning system that would mitigate that.
Yeah, we're in the same boat. I don't have much to add.
The solution I saw that I thought was interesting and was the I think it's the chilled iron solution, where they pull the water through the system. So if there's a leak, they're just essentially pulling air into their fluid network, which obviously creates its own challenges. But I could see at least the customers we're working with find that pretty attractive. But I guess, if you're going to bring water right to the chip, you've got to have a little bit more risk tolerance than if you were going to just go straight air cooled, right? I mean, so that decision speaks highly of your appetite for water in the space.
I'll jump in real quickly at the server level. There's been a lot of improvement in this space. These are not, your gaming systems that are going into servers. These are systems that have been hardened, that have been tested, to colder than you'd ever run it and hotter than you'd ever run it, and cycling back and forth and shock and vibe, the whole 9 yards. And so, we'll see what the statistics actually show, but we believe we're approaching, really good reliability at the cold plate level. In addition, there's a significant number of improvements in leak detection. For instance, Dell has put out a new, or actually since last generation, put out a leak sense technology that senses incredibly small leaks at the chip and notifies the user immediately to eliminate or minimize what we call the blast radius, what might occur from a leak. We are innovating in some really cool ways that I can't talk about improving and increasing the coverage of that leak detection and you know, not just in the server, but even potentially to the rack and row level, so that we can provide very early notice if there is a problem. So I just want to, you know, it is a risk for sure. There have been leaks for sure, but the overall number, you know, Dell has actually shipped tens of thousands of liquid cooled servers, and the total number of leaks are a very, very small percentage of that, and we're continuing to improve to the early warning system for users to react and limit any sort of damage to that.
And Tim, for those type of applications, does Dell provide advice or installation of the facility or the secondary fluid network? Do they typically give you kind of a direction on that, or?
Yeah, so we have partnered for years with a specific partner who will come in and if you know, we can provide that service through our partner of actually designing a secondary fluid network that has been tested and is known to be, you know, a reliable system. If the facility chooses to design its own, we can absolutely provide guidelines as to what that should look like and what the parameters should be to provide sufficient flow, prevent contamination, and so on. Yeah, that's part of our role when we work with our customers to deploy liquid cooling.
And then you mentioned one other thing, you dropped the blast radius words in there. And so one of the things that we've struggled with, and I know I've spoken to Keith about it, is from a redundancy perspective. You know, typically we're building with a number of air handlers in the data hall galleries, and it's usually N+2, sometimes higher. What are you guys using when you're saying CDUs or your secondary fluid network? What are you sort of talking in terms of redundancy blocks?
So this varies quite a bit, varies with the comfort level of the customer. At the CDU level, most CDUs are designed with N+1 redundancy on everything that's critical to cooling. So not just pumps, which are typically 2N, but also valves and valve controllers and sensors and everything that if it failed, you would have a cooling fault or a leak is typically N+1 redundant inside the CDU. That I can't say that's 100% statement, but that's a high percentage of CDUs that are delivered. So typically, actually, we don't recommend doubling up CDUs unless there's a desire to do that for future growth. But from a reliability standpoint, CDUs that are shipping today tend to be very reliable on their own and often enable hot swapping of pumps and other parts while the system is running. So again, check with a specific manufacturer to ensure that that's possible. Not every model is, but you would possibly be surprised at the serviceability of these units today, and the ability to keep a secondary fluid network up and running even while replacing something as big as a major pump.
Sorry to say, guys, we're out of time. It's been a great discussion. I thank you to all the panelists. And now I'd like to turn it back over to Alex, and we'll move towards Q&A from the audience.
Thank you for a great panel, everyone, and thanks for moderating, Keith. Thanks again to those who sent in questions. A reminder, we'll be holding live Q&A at 12:15 p.m. Eastern Time, when we'll be tackling all of the questions. Next up, we have a technology-focused session, during which Mike Herwald will explore how adaptable and efficient the cycle split system is. We'll see you in a few moments.